Nice to meet you. I'm Prof.Joun, working for GNU in Korea. In this lecture, we are going to study how to remove the essential boundary condition and or geometry condition out of boundary value problem. For more knowledge about this topic, you'd better be advised by any related books, including this reference. Also, I hope you to take a look at not only the approximate method of boundary value problem, but also the Lagrange multiplier method and parallel method to remove the equality constraint in nonlinear programming problem in the finite dimensional vector space to be ready to listen to this lecture. This topic is important, particularly in advanced mechanics, including metal engineering and fluid mechanics, where the equation of continuity should be dealt with. It is because even though this lecture only deals with the removing scheme of essential boundary conditions, the same approach can be applied to remove the geometry conditions involving the equation of continuity. This is the basic principle with these two essential boundary conditions. They can be removed using Lagrange multiplier method like this. The original base principle is transformed into the augmented base principle without any equality constraint like this. In this new base principle, a function lambda is unknown and defined only at the boundaries. We can thus treat the lambda function as constants at the boundaries, that is, lambda 0 and lambda 1, which can be denoted by just unknown constants. For example, A and B. However, for generality and extensibility to 2D and 3D cases, we will use this expression using lambda function in this formulation. Now, let's obtain the Euler-Lagrange equation applying the first derivation to the new functional. For this necessary and sufficient condition for this functional to be stationary, we obtain the Euler-Lagrange equation and physical meaning of the lambda values as well as the boundary condition at once. Now let's solve the same problem we have studied previously, starting from this extended base principle. Assign two trial functions, like this for a known function phi x, and like this for a known function lambda x, with emphasis on its values at x equals 0 and x equals 1, that is lambda 0 and lambda 1, respectively. We don't have to consider any boundary condition now in this case. Substituting these two approximations into this extended base principle, we obtain this function of 4 ci's and 2 lambdas. Applying this necessary special condition to make this approximated function weakly stationary, we obtain a set of 6 linear equations for the 6 unknown constants, resulting in these solutions. Plugging these solutions into the trial functions, we obtain this approximate solution of the known function phi x, which is identical to Ritz or Galerkin approximation. From lambda values defined at the boundaries, which have mathematically a relation with physical meaning of slope, we can obtain the slopes at the boundaries, which are exact, as explained here. Of course, we know that we cannot obtain the exact slopes from this approximated solution. That is, the approximate slopes calculated from this approximate solution are 1 over 15 and minus 7 over 30, which are different from the exact solutions of this and this, respectively. Of course, Lagrange multiplier method increases the number of known variables, so it gives us the improved solutions at the expense of computational inefficiency and a little theoretical difficulty. Now let's study so-called modified Bayes principle, plugging the physical meaning of lambda into the extended Bayes principle. Let's replace the lambda 0 and lambda 1 by phi prime 0 and minus pi prime 1 respectively to obtain this modified Bayes principle, which does not involve any essential boundary condition and any unknown function or constant except for the major unknown function phi x. Now let's practice an example starting from this trial function. Plugging this trial function to this modified Bayes principle, we obtain this function of its stationary point should be found. Applying this condition, we obtain this set of 4 linear equations, which gives us this approximate solution. This figure compares this approximate solution with the exact solution, showing that much error exists between them. It can be also seen that the approximate solution does not meet the essential boundary conditions imposed on both the ends. However, we can check that the slopes at both the essential boundaries are exact. Anyway, it is very interesting to obtain an approximate solution from this simple modified Bayes principle, which predicts more accurate values of its derivative at the essential boundaries at the expense of solution accuracy of the known function, including the essential boundary conditions. Now, let's study how to embed the essential boundary and or geometric conditions into weak form using the same boundary value problem. This problem can be reformulated using arbitrary function omega x and another arbitrary function omega bar x. This omega bar function is meaningful only at the boundaries. However, we consider omega bar as a function for generality and extensibility to 2D or 3D problems. We apply the same mathematical treatment to this formulation to reduce the highest order derivative and get this relation. It is very difficult to assign some constraints on omega or omega bar function at the boundaries directly from this integral equation. We'll better obtain some insight from the modified Bayes principle, which is mathematically straightforward. Comparing this relation with its first variation stated here, we can assume that omega bar at left end equals omega prime 0 and omega bar 1 at right end equals minus omega prime 1. Substituting these assumptions, we obtain this modified weak form, which does not involve any constraints. And there is another way of removing essential boundary or geometry conditions, that is penalty method. The same principle is applied to remove the equality constraint in nonlinear programming problem to find the discrete extreme points in finite dimensional vector space. To remove these two essential boundary conditions out of the Bayes principle corresponding to this boundary value problem, we added these two terms that are penalty terms to replace these boundary conditions. Beta function is meaningful only at the essential boundaries. However, we have kept to use this function expression just for generality and extensibility as we did previously for other cases. Beta function should be of a large value and is assumed like that in many cases. Now we start from this trial function without any consideration of constraint together with a large constant of 1000 for the penalty function values at both the ends. Substituting these approximated unknown function and penalty values into this new variance principle, we obtain this function of only CIs. Applying the nested condition to the approximated function, we obtain this approximate solution. This figure compares the approximate solution with the exact solution. You can see that the approximate solution is very similar to the Ritz or Gallatin approximation, even though it does not meet the essential bound conditions, because of this term at the left end, for example. Of course, you may think that the penalty function or constant relates some state variables to the physical meaning, as we know that lambda in Lagrange multiplier method has a relationship with slope at the boundaries. Applying first variation to the extended variance principle, you can derive a mathematical relationship between some state variables with any physical meaning, which are linked by the penalty functional constant. Please try to obtain the relationship by yourself. Now, I'm going to summarize this lecture, covering the related lectures on approximation of boundary value problems. This method can be applied only to the case when variance principle is defined, while the weighted ledger approach can be applied to any kind of boundary value problems. Of course, canonical approach is one of weighted ledger approaches. However, it is superior to any other approximations under the name of weighted ledger approach, particularly for finite formulation. So Gallatin approach is sometimes used as the representative of weighted ledger approach in FEM. The traditional Gallatin approach and this method are limited because of difficulty in formulating trial functions satisfying essential bound conditions, especially for practical engineering problems on the two-dimensional plane or in three-dimensional space. This problem concerned with trial functions can be solved by finite element approximation, that is, finite element discretization and finite element interpolation. This and Gallatin approaches are the mathematical backgrounds of FEM. FEM needs only an additional technique to prepare the trial function in a systematic way based on digitalization concept with the application of computer. There are two major ways of FEM. One is the variation approach, that is, this approach to FEM, and the other is weighted ledger approach, that is, Gallatin approach to FEM. The Gallatin approach to FEM is more general because there is no theoretical limit.